Yeah, so first I'd like to thank the organizers for this opportunity to discuss this first result from the G-2 experiment. So the G-2 experiment is basically being used to study spin-based physics. Muons have intrinsic spin and charge, and so they produce a magnetic dipole moment. And so you see here this equation basically relating the magnetic dipole moment and the spin. And what we're interested in here is this constant here, this G factor, which is basically just a proportionality constant between the spin and the dipole moment. And you can basically rewrite it so that you have the Muon anomaly, which encodes the deviation of G from 2. So in Dirac theory, A is exactly 0 and G is exactly 2. But in the standard model, A is greater than 0, and so G is greater than 2. And the reason that A is non-zero is basically due to vacuum effects. And so sort of the leading order Feynman diagram here showing the muon interacting with an external magnetic field corresponds to the Dirac theory, but then you have QED corrections, electroweak corrections, and hadronic corrections. And so the thing that's interesting to note is that QED is the largest standard model contribution to the muon anomaly, but since it's relatively straightforward to do calculations in QED, it ends up contributing the smallest uncertainty to the standard model prediction. And so it's not really a surprise, but it's the QCD based contributions that end up being the largest sources of uncertainty in the standard model prediction. So on April 7th of this year, the Muon G-2 collaboration released its first Fermilab measurement of the muon anomaly. And so we were all happy that basically the Fermilab measurement here is in agreement with the BNL final result. It's useful to note that this agreement here is basically being driven by statistics, and so if you see these little tick marks here, that's basically showing you the difference in the contribution from the statistical here and the systematic to the uncertainties. And so this agreement is being driven by statistics and not getting all the systematics correct. And so if you combine both of the measurements together, you get this here. And when you compare it to the standard model prediction from the recommended value from the Muon G-2 theory initiative, you end up with this interesting 4.2 standard deviation difference between the standard model prediction and the measured value. So as you can imagine, there's a lot of exciting work going on with people updating the standard model prediction of the muon anomaly. Our collaboration's plan is to compare the measured values to the Muon G-2 theory initiative recommended values. This theory initiative is continuing to do updates for the recommended value. It's important to note that there's this recent BM-W20 result. It's the first lattice result with a sub% uncertainty. And so if you look here at the G-2 theory initiative recommended value, you can see there's a bit of tension between the two of them. And so there's an ongoing discussion in the community to understand this difference. So my focus for this talk really is just to explain how the measurement was done. So at its core, the G-2 experiment is basically a frequency based measurement. And so if you consider the ideal case here, where the muon motion is perpendicular to the magnetic field inside the storage ring for the muon beam, and the electric field is 0, what you end up having is your spin ends up precessing in the plane of the orbit. So this is shown here in this cartoon in red. And at the same time, you have these muons moving around in a circle. And so basically their momentum is also rotating in this plane of orbit. And so you can consider this difference frequency here, omega A, that we call the anomalous precession frequency. And so you can see that it has a simple relationship to the muon anomaly, which is the physics we care about, and then the magnetic field that's being seen by the muons. And so just to be clear though, the experiment actually measures a scalar frequency, not a vector frequency. And so everything sort of boils down to this simple equation here. So we also have to end up measuring another frequency in the experiment. And so, as I mentioned, in this equation, we have the magnetic field, and we use NMR to measure the magnetic field. So then we're basically measuring the proton Larimar precession frequency due to that magnetic field. And so we have this R ratio of frequencies here, and then we can basically combine it with other physical constants to get the muon anomaly. And so the thing to keep in mind here is that it's the uncertainties from our experiment that's really driving the final uncertainty on the muon anomaly, and not uncertainties on these other terms here. So our final error goal is 140 parts per billion, but when you look at these other terms, they have uncertainties that goes 10.5 parts per billion. There's an exact QED correction here, 22 parts per billion, and 0.28 parts per trillion. So sort of the basic fundamental underlying principle of how we're actually able to see the anomalous precession frequency in decay positron spectra is due to the properties of the weak decay. And so when muons decay, there's ends up being a correlation between the muon spin at the time of the decay and the direction of the outgoing decay positron. And so it's natural to think about this in the center of mass frame of the decay, or the rest frame of the muon, but we don't measure the positrons in the rest frame. We measure them in the lab frame. And so basically we end up measuring boosted decay positron energies. And so if you look at this little movie here, what ends up happening is the relative orientation of the muon spin relative to the lab frame momentum of the muon ends up producing a variation in the energy spectrum of the decay positrons. And so what ends up happening is if you apply an energy cut to the decay positron data, you end up seeing this modulation on top of the expected exponential decay of the muons. And so then the other part, as mentioned previously, is that we need to know what the average magnetic field is seen by the muons. And this is really a two-step process. So one step is that we need to actually measure the magnetic field seen by the muons in the storage region of the ring. And so we use NMR to do that, but then we also need to actually measure the distribution of the muons. And we use straw tracker detectors to do this. And then we combine those together then to get the average magnetic field. So just sort of big picture a little bit before I get into more of the details of how the measurement's done. This experiment to save on construction costs ended up reusing the BNL storage ring. And so the storage ring was moved from Brookhaven to Fermilab. One of the advantages of Fermilab is that we're able to get a more intense, cleaner polarized muon beam. Our goal our fundamental or our ultimate goal is to reduce the overall uncertainty on the measured value of the muon anomaly by a factor of 4 with respect to the BNL measurement. And so this would be bringing it down from 540 parts per billion to 140 parts per billion. And so, this requires us to collect basically 20 times more muon statistics. And also too, this isn't just a repeat of the Brookhaven measurement. There's been improvements and upgrades that have been done. And so, our systematic uncertainty goal is being moved down from the 280 parts per billion from Brookhaven down to 100 parts per billion for this measurement. And so, it's not the largest collaboration by particle physics standards, but we do have more than 200 collaborators from 35 institutions in 7 countries from around the world. And so the experiments being done at the Muon campus at Fermilab, right now there's 2 experimental halls on the Muon campus at Fermilab. There's the MUE building, and then there's the G-2 building, and they basically just sort of sit behind Wilson Hall at the lab. And so here is just a picture showing everything put all back together again. And so now I'll go through a little bit the mechanics of the measurement. And so we begin with a highly polarized muon beam. And in the experimental hall, we have these magnetic quadrupoles that are part of the final focusing for injection into the storage ring. And then we have this special superconducting magnet that we call the inflector. And so this is what we use to basically channel the beam into the storage ring. And so you can sort of see here in this cartoon, the issue, the first issue is that they're not on storable orbits. So basically we did nothing, the beam would come around and end up hitting the vacuum chamber of the inflector. And so to get the muons onto storable orbits, we use these 3 magnetic fast kickers, they're non-ferrous, to basically deflect the beam onto storable orbits here. And then we need to use electric quadrupoles to provide weak vertical focusing. So, the magnetic field that we're using for the physics basically provides us the radial confinement that we need for the beam, but it doesn't provide vertical confinement, and that's why we have to use these quadrupoles. So, as I mentioned before, we need to measure the distribution of the muons to get the average magnetic field seen by the muons. And so we have these 2 tracker stations that we use to do that. And so basically what happens is you have a muon in the storage region of the ring decay, and it produces a decay positron that ends up going through straws. And so we're basically able to reconstruct its trajectory in the straws, and then we extrapolate that trajectory back to where the muon decay occurred. And so then to measure the anomalous precession frequency, as I was saying before, we have a decay positron spectrum, but we need to apply an energy cut to get the modulation that we want. And so we do this with calorimeters that then measure the arrival time and energy of positrons that strike the calorimeter. And each of these calorimeters are made out of a segmented array of 9x6 lead fluoride crystals, and there's 24 of them placed uniformly around the inside of the storage ring. And so then to measure the magnetic field, basically every 3 days, we stop taking beam, and then we move this device that we call the trolley around the storage ring. Basically, it ends up sitting inside of the storage region where the muons live, and it lets us measure. The trolley contains 17 NMR probes, and it lets us do 2D field maps at about 9,000 azimuthal locations around the storage ring. So you might ask, how do you know what the magnetic field is when you are taking beam and you're not using the trolley? And so we have a large number of what we call fixed probes, and these are NMR probes that sit in grooves on the outside of the vacuum chambers and the top and the bottom of the vacuum chambers. And so basically, the trolley probes in these can operate all the time, and so we're monitoring the magnetic field when we're taking beam. And so the trolley probes basically act as a calibration for these fixed probes. But then there's a further calibration step. We have a calibration probe that basically we usually call it the plunging probe. And so what you can do is you can stick that into the a spot in the storage region, and then measure what the magnetic field is, retract it, and then move a trolley probe into the same region, and then measure the magnetic field, so you can have a cross calibration. And then this calibration probe is then further studied at a test magnet at Argonne National Laboratory to get a final calibration factor for the magnetic field. And one of the upgrades actually for this measurement compared to the Brookhaven one is some of the collaborators developed actually an absolute helium-3 magnetometer that's also used as a cross-check calibration probe. Okay, so now I'll discuss a little bit how the analysis of the data works. And so, I showed you this relatively simple equation up here where we need to measure these two frequencies, the anomalous precession frequency and then the NMR frequency for the magnetic field. But things, of course, in practice are a little bit more difficult. And so, in the numerator, we have this F clock term that's basically a blinding conversion factor, which I'll discuss on the next slide. As I was talking about before, you have to do, we need an absolute NMR calibration factor for determining the magnetic field. We measure, we use decay positron spectra to measure the anomalous precession frequency, but then we actually have to apply corrections to get, essentially the true anomalous precession frequency. And so, for instance, we have this electric field and picture corrections that we have to apply. This is basically due to spin and beam dynamics. Basically we operate at what we call the magic momentum, which helps minimize the electric field from the quadrupole focusing. But of course, we don't have muons that are all perfectly this magic momentum. And so we have to take that into account and correct for it. And also too, we have, pitching motion or, betatron motion of the muons, which again ends up causing an effect that we have to correct for. We also have some detector-based effects, and so we have a spin momentum loss muon and phase acceptance corrections, and that's basically due to detector acceptance effects, affecting the G-2 phase that's associated with the anomalous precession frequency. And as I mentioned before too, we have to combine together essentially the magnetic field measurement and the distribution of muons. And then also we have to apply a couple of magnetic field corrections due to kicker eddy currents and quadrupole transient effects. And so just to show you some of the numbers, the Run 1 data set is actually was broken down into 4 subsets. This was due to different quadrupole and kicker settings, but you can see here that all the numbers turn out to be very similar to each other, despite the different settings. And then here's a breakdown of correction terms and the size of the corrections, as well as their associated uncertainties. So I don't have time to cover everything, so I will discuss a little bit more the 2 largest sources of uncertainty for the Run 1 measurement. So we do a blind analysis for this measurement, and so we use a single 10 megahertz GPS discipline master clock to measure the frequencies, and the anomalous precession frequency analysis uses this hardware blinding, which is basically detuning the clock to within a range of plus or minus 25 parts per million. And so we basically have two people who are not actually collaborators are the ones who come up with the blinding factor and then check the clock weekly to make sure there isn't drift. And also too, we separately blind each run's worth of data. And so this allows us to sort of analyze, do analyses, run by run independently. And so these conversion factors are actually held in secret envelopes, sealed envelopes, that a copy of it's held at the University of Washington, another one at Fermilab. And so for the run results, we actually did a collaboration-wide vote when we were ready to unblind or not, and this was actually done February 25th. I should also mention too, there's actually another step, another layer of blinding that we actually do. And so before we're ready to do the hardware unblinding, we also, the analyzers, individual analyzers apply their own personal software blind to their analysis. And so we have this step where, when basically people are happy with their analyses, people then remove their software blind, and so then we can do a relative comparison for values between different people's analyses before we are ready to do the hardware unblinding. Okay, so to determine the measured anomalous precession frequency, the physical signal for this is described by what we call the 5-parameter function, and so it contains a normalization term and what we call the asymmetry term, and this is basically the amplitude of the modulation with respect to the anomalous precession frequency, which is what we want to determine. And then there's this corresponding g-2 phase. And so, as I mentioned before, the parameters of this function depend on the energy cut we apply to the decay positron spectra. But of course, in reality, things are a little more difficult. And so we have these detector acceptance effects, which basically turn these 3 parameters into functions of time as well. And so these parameters end up depending on the beam frequencies of the muons inside the storage ring. And we also have the issue where the normalization term here depends on muon losses. And so, since this is a high precision measurement, we make an effort to have, independent analyses when we determine omega A. And, these different analyses actually, depend on 2 different clustering algorithms. And there's also variations on the analysis that you can do. So there's different methods. And so multiple methods are used when determining omega A. And so if you look here on the left-hand side, you can see you have these fit residuals. So this is where you just fit, where you basically don't take into account the detector acceptance effects. You're just using the 5-parameter function. And when you look at the fit residuals, you can see here, even by eye, it's very obvious that you still have a frequency in your fit residuals. And if you actually look at the FFT of the fit residuals, you can see frequency spikes clearly in the data. And so when we do our fits, we obviously want to get a good chi-square per degree of freedom. But since we're trying to very precisely measure a frequency, we also don't want to have frequencies in the fit residuals. And so when you basically put in all the systematic effects, you can see here that we do end up with a good chi-square per number of degree of freedom. But then also when you do the FFT of the fit residuals, you can see that you get rid of the frequency spikes in the data. And so, so just sort of for example here, there's a couple of effects I wanted to mention that we need to take into account when measuring omega A. from the decay positrons. One important effect that has to be accounted for is pileup. And so basically what happens is two or more low energy positrons hit the calorimeter too close in space and time. And so they basically get reconstructed as a single higher energy event. And so, remember, again, we're seeing this modulation because we apply an energy cut. And so if you have, this event, which we think is a single event above the energy threshold, including these events ends up distorting the time and energy spectra. And so this is, particularly a problem too, because you're most likely to get pileup, right, at early times when the rates are the highest. But this is also where the most statistics are in your distribution that you're fitting. And so, getting this part of the distribution wrong is right. You're more likely to end up pulling the omega A that you're trying to measure. And so you can even see here from this spectrum, pileup spectrum, we expect to have events, positron events with about 3.1 GeV or lower. And so you can even see here that we have a small number of events above this, which we know, right, are basically non-physical from the physics of the decays and the boost, the Lorentz boost to the lab frame. So another effect that we have to include in determining omega A is muon losses. So we can basically have muons in the storage ring basically escape and leave the storage ring before they decay. So if we only had muons decaying, then we just have exponential decay. But since we have these losses, we end up with modified exponential decay. And so we can actually measure these losses and then use that measurement as part of our fit function. And so we're able to measure the muons by looking for triple coincidences in 3 adjacent calorimeters. And so basically, here's this cartoon showing a muon leaving the storage ring, and it can pass through 3 adjacent calorimeters, and then it produces a MIP in the calorimeters. And so by looking for these coincidences, then we can be very confident that this was an actual lost muon. And then so sort of to end, I want to mention also this quadrupole transient effect. And so what's going on here is we have these electric quadrupoles that we need for the vertical focusing. And so we have to end up pulsing these quadrupoles. And so sometimes you might hear someone talk about electrostatic quadrupoles, and what they mean is the quadrupoles need to be static when we have beam present. But if we ran them in a true DC mode, we would end up with a spark rate that would be too high that would interfere with our ability to collect data. And so we basically have to power the quadrupoles off when we don't have muons present. And so this is why we're pulsing the system, and it ends up inducing mechanical vibrations in the quadrupole plates. And so the issue then is you have a moving metal parts inside of a magnetic field, which is then going to generate a magnetic field, which then distorts the field that we're using for measuring the physics. And so to deal with this, we built customized NMR probes to basically measure the effect. And this was done at several positions within one of the quadrupoles, and it was done at the center of the other quadrupoles. And so if you look over here in this upper right plot, you can see basically the field distortion that's being produced. Now, if you look at this, you're getting plus or minus 400 parts per billion, which looks scary. But what you have to keep in mind here is that the muons are only present in the gray bands. So you're not seeing all this variation when the muons are actually present and when we actually care about what the field is. And so you can see in the zoom in here, you actually end up with a lot less variation when the muons are actually present. And furthermore, when you start averaging over muon bunches, you're going to get some cancellation, and so then the overall effect is actually a lot smaller. Now, going forward, we expect to improve our understanding of the systematic effect by a factor of 2 to 3, because basically we're going to do more measurements to better understand, the effect for run 2 on. So then, in conclusion, I'd like to point out that we've actually already published 4 papers for the run 1 measurement. You can get them on the archive. We published them in Physical Review. And so we have a paper in PRAB discussing the beam dynamics related systematic effects. In PRA, we published a review of the field measurements. In PRD, we have a review of the omega A measurement. And then finally in PRL, we have a summary of everything. So then in conclusion, we released our first measurement, so we're all very happy about that. I'd like to point out that this run 1 data set is actually a small fraction of the total amount of data that we're going to collect. So basically, we're going to collect an order of magnitude more data than what's in this first measurement. We're actually also are making several other measurements. We're able to use the data to test CPT Lorentz invariance, as well as measure the Muon EDM. So right now we're analyzing the run 2, run 3 data. We're basically just finishing up collecting our run 4 data, and we will have a run 5. And so.
Great, thanks a lot for the summary of this incredible measurement. We went a bit over time, but we're happy to take questions. Perhaps while people are typing, just out of curiosity, is this order of magnitude data, is that including run 5, or are details about this still being settled?
That will include, I'm trying to think, I think we already have it, really.
Okay.
Yeah. Sorry, I'm just trying to think through, because we still have to apply data quality cuts, but I think we already have it, I believe. We should already have it.
Okay. We have our first question, which I think you touched on a bit already at the beginning, but it's about the new lattice QCD calculations that showed closer agreement.
Yeah, I'm sorry. What was the actual question?
What about them?
Oh, sorry. What about them? Yeah, this is the sort of thing where, as I was saying, really the theorists have to have this discussion, because, there's these techniques that they've been using for decades now, that are in part based on cross-section, E plus E minus cross-section measurements for determining the hadronic vacuum polarization contribution. And this is this first, sub% level, lattice prediction. And so, this is something that they're having the discussion to understand why there's sort of a tension between this technique that's been around for a very long time, in this new precise, calculation.
That's clear, thanks. We have another question, which is, what is the key difference between your experiment and BNL?
So I would say it's probably the detectors. So the ring itself, basically was reused. We did have to rebuild our kickers. The quadrupole system, parts of it are reused, but upgrades were done. But we have all new calorimeters And as I was saying too, for instance, one of these important corrections is pile up, and they're actually segmented to help reduce the pile up. We have a laser calibration system because you end up having lots and lots of channels because we have 9x6x24 channels, and so we have a sophisticated laser system to keep everything calibrated. Also, too, these straw trackers, they did not. These straw trackers actually sit within the vacuum system. The BNL experiment, had a system that basically did the same thing, but it actually sat outside the vacuum system. And the trackers let us, do basically, a lot of, beam measurements while we're actually taking data. And so this helps us a lot, understand, what the beam is doing and the frequencies. And all that, which is again important for doing precise frequency measurement.